Thank you, everyone. So welcome back. So we're ready to continue with the rest of the track 3 papers. The next paper is titled A Methodology for Evaluating Silicon Artifacts in DDR4-3DS PHY using Channel Modeling. This paper is from Samsung Electronics. The author is Anil Deshpande. We also have Shivani joining us for the Q&A session. Okay, so on to the paper presentation.
Hello everyone, I am Shivani Maurya, member of the PHY DV team at Samsung Semiconductor India R&D Center, and today I am here to present a novel methodology for verification of PHY IP for DDR4-3DS memory. A quick look at the agenda before we dive into the details. I will begin by providing a primer on the current industry landscape, followed by an overview of the DDR4-3DS memory. I will then discuss our approach to verification and why we felt the need to model effects like noise, skew, damage, and distortion during the verification of DDR5. What were our considerations in building each feature element and how we parameterized them? The test bench architecture used for verifying the DDR5 would be discussed, and I will provide the details on how the channel model and the alignment checkers helped us in finding bugs early in the design during the verification of the PHY and gave us more confidence on design verification. I will end the presentation with a brief discussion of the future scope and followed by the questions from the audience. The amount of data to be processed has exploded with networking. We are at a critical juncture where new technologies are rapidly undergoing improvements. It is not surprising to find that the memory footprint has increased manyfold, and the industry has been aiming for higher throughputs and higher bandwidths. The advanced fabrication techniques have made the miniaturization a reality. The length of the channel between the source and the drain, which defines a technology node, has been decreasing over the years. It is quite evident from this roadmap of different companies shown here. At present, we have transistors as low as 4 nanometer technology node, with sub 3 nanometer on the horizon. With decrease in the technology, however, new geometries have come into play. The transistor evolution has gone from the classical planar FET to planar double gate to FinFET. The push towards the sub 3 nanometer technology is currently driving the development of the complementary FETs as we speak. Within 2 decades, all computations have come to rely heavily on memory, so much so that it often becomes a bottleneck in the performance. The need to make them even better has driven the revisions of memory protocols over the years. The JEDEC organization, which specifies the DRAM standards, has defined 3 categories based on the power, performance, and the area requirements of the target applications. There's a standard DDR. The famous protocol in this category is the DDR4, and the DDR5 being the next iteration. It was made available last year. The second is the mobile DDR. The popular standard in this category is the LPDDR4. And the third is the graphics DDR. HBM and GDDR are the popular standards in this particular category. Now we will look briefly into the DDR4-3DS memory, which we use for verifying DDR5. DDR4-3DS stands for double data rate 4th generation 3-dimensional stacked memory. A conventional stacked solution like DDR4 consists of a redistribution layer which redistributes the signal to different dies using bonding wire, thus providing high loading. In contrast to this, the TSV solution like DDR4-3DS offers an etching technique which it uses to connect the master die, which is the bottommost die, to the other slave dies. The master chip is the only interface on the stack which communicates with the memory controller over the data buffer on the LR DIMM. TSV is an effective solution for achieving more capacity in less unit volume without adding bus loading as compared to the conventional solution. It has improved the turnaround time due to seamless writes and reads, higher bandwidth and superior energy efficiency as compared to the multi-rank solutions. The structure of the 3DS devices means that there is a potential for intra-stack operations to happen with less delay than the inter-rank operations. The different ranks in the DDR4 3DS are actually the logical ranks. The logic ranks are selected by the chip select signal, and each logical rank has bands and band groups. The rapidly changing landscape of the VLSI design industry and the complex architectures in the latest memory design present a lot of challenges to the verification engineers. The verification environment needs to be robust and cater to the changing trends. There is a need to find bugs early in the design so as to avoid multiple respins. The strict time to market constraints mean that there is a requirement of high quality design and there is a high quality verification. We need to adopt latest verification practices and methodologies and enhance our own knowledge base. As a general practice, all the verification engineers keep these challenges in mind when they devise new ways to improve upon the traditional verification practices. With higher density and stacking, as discussed in the DDR4 3DS overview, interconnects have come even closer. This makes the effects of skew and distortion highly significant. Because of this close-knit structure, even slight variation in the nature of the signal becomes a cause of concern. To us, this threat to signal integrity during the verification of DDR5 seemed like a warning bell. It became imperative for us to find a way to stress test our PHY, which led to the development of our in-house channel model, supplemented by our alignment checkers. Today, we can confidently support the industry solutions with lowered chances of unwelcome surprises in the post-silicon stage. Now we'll look into the memory subsystem, which consists of the memory controller and PHY, and they interact with the memory. The signal is affected by factors like temperature and voltage fluctuations, the noise, interference, etc. These factors manifest in the form of skew, distortion, glitch, and crosstalk. In order to account for these factors during verification, we have developed the in-house channel model, which is a UVM compliant component. The commands which are sent from the memory controller, they are sent through the channel model, where the user specified effect is applied on top of the signals before passing them on to the memory. The same thing happens in the reverse. When memory has to send something to the memory controller, it passes through the channel model where the desired effect is applied and then only passed on to the memory controller. Having a channel model enabled us to find bugs arising during this communication, the bidirectional communication between the memory controller and the memory through our PHY. We will now proceed further and learn more about the design of the channel model and how it was used in the verification. Here we can see the test bench architecture that was used for verifying the DDR5. The memory controller uses the DFI protocol to communicate with the design under test, that is our PHY. The PHY translates the DFI protocol to the memory protocol and transfers it to the channel model, which applies the disturbances and then transmits it to the DDR4-3DS memory. The DDR4-3DS memory also routes the commands through this channel model before sending it to the PHY, which then translates the memory protocol back to the DFI protocol. We have used the verification IPs provided by EDA vendors for the DFI and the DDR4-3DS memory component. Assertion checkers have been used for checking the PHY functionality along with coverage, monitor, and scoreboard. Now we will look into the channel model in detail. Our in-house channel model has been developed as a UVM component. The parameters allow configurability in terms of the maximum and the minimum skew or damage that can be applied, while conforming to the JEDEC timing parameters and the design specifications. The different features are generated by approximating the manifestation of effects in the digital time domain by using UVM constructs like always, forever, etc. The top level view of the channel model that can be seen here shows that the signal 1 is the input and signal 2 is the output. This output is the signal on which we see the desired effect. when it is enabled inside the channel model. We will see the different modified versions of this particular signal to see the effect of features available in the channel model in upcoming slides. So how did we use this channel model element? We basically instantiated one channel model element per interface signal. So clock signal had its own channel model instance, the data line DQ had its own channel model instance, and so on. The instance can be made to affect either the drive path or the receive path depending upon the requirements. The block level parameters like the width of the signal, the rank, the drive and the receive qualifiers, and the feature enable make sure that only the desired effect gets applied on top of the signal. It is possible in our channel model to enable multiple features at the same time if required, but the condition is that at all times these effects should be dictated by the JDEC and the design requirements. An arbitrarily high value without considering the limits set by these specifications is not advisable and not relevant to verification. Here we can see the visual of the different features supported by the channel model. It shows the output from the channel model with the desired effect enabled. This is the ideal output when none of the features are enabled. This is the skewed output when the output is shifted with respect to the original signal. The distorted output shows the distortion applied to the left and the right edges of the input signal. The duty cycle distorted signal shows the decreased duty cycle variant of the original signal. It is also possible to increase the duty cycle if required. And this particular output shows the glitches added to the original signal to stress test the design. When output of one block is given as the input to the next block, skews may be introduced. The channel model is used to model these skews. Here we can see that the skew is manifesting on a signal as the delay. So this skewed signal has been delayed from the original signal by a value specified by the user. For verification, user can randomize this particular value within the limits which have been set as parameters inside the channel model element. Channel model allows the user to also define relative skews between two signals, which can have their own inherent skews. Distortion, on the other hand, can occur due to noise and signal interference. Channel model can be used to add distortions to reduce the valid window margin of a particular signal. The left and the right window distortion can be seen here, reducing the valid window margin of the original signal. This distortion can either be X, Z, 1, or 0, and the value has to be within the specifications. Distortion can also be applied using crosstalk. Channel model simulates the inductive and the capacitive interaction between neighboring wires. So the crosstalk feature actually compares the value of each bit with its neighboring bits. While we have restricted our neighbor count to 2, this count can be varied depending upon the requirements. Considering the example here, we see that for calculating the crosstalk on bit 5, we compare its value with its two neighbors on either side, and only one neighbor, that is bit 7, has its value different from bit 5. This means that the score for bit 5 will be 1. This particular score is then multiplied by a scaling factor to get the dynamic noise for that particular bit. The duty cycle of a signal can be varied due to temperature and the voltage fluctuations. We simulate this using our channel model by varying the on and the off states of the interface signals. Here we can see that the original signal has a duty cycle of 50%, whereas the duty distorted signal has its duty cycle decreased in this particular region and increased in this particular region. The percentage increase and decrease can be configured by the user. The channel model allows a user to also introduce glitches onto the original signal. The user can specify how many number of glitches are required in a particular unit interval, or he can also decide the pulse width of the signal, of the glitch that has to be introduced. Once we were done developing our channel model, we needed checks to make sure that the phi behavior was consistent with the expectations, even after the channel model effects had been applied. Depending upon our requirements, we introduced two types of checkers, the edge alignment checkers and the center alignment checkers. Ideally, what we mean by edge alignment is that the positive edge of two signals would exactly coincide. And by center alignment, we mean that the positive edge of one signal will exactly coincide with the center of the other signal. So when do we use these checkers? These checkers would come into play only after the relevant calibrations have been done in the presence of the effects applied by the channel model. The intent behind these checks is to make sure that the phi functionality was not impacted by the distortions and effects added by the channel model. Failing any of these checks would mean that the phi behavior was not up to the mark. This could either mean bugs in the design, or it could mean that the design specifications need to be revised. Both cases are of interest to the verification engineer. We need to stress test our design to its limits, but we also need to set those limits to the best of our knowledge through rigorous testing. Till now, we have covered how the channel model was developed and the different features which are supported by it. Now we will look into the actual application of the channel model. Here we can see the interface connections between the DDR5 and the DDR4 3DS memory. Inputs to the memory are the clock signal, the clock enable, the ODT, which is the on-die termination, the chip select, the chip ID, the address strobe signals, the bank group, the bank address, etc. The bidirectional signals are the DQ, which is the data line, the data strobe, which is DQS, masking, DM, DVI, etc. The features supported by the channel model can be applied to each of these interface lines independently. There's user configurability to apply skew or distortion rank-wise or in a random fashion. For the purpose of illustration, we will be using DQ signal and apply features on this particular signal to show the effects as applied by the channel model. The read and write calibrations are performed in order to achieve the maximum window for the data I. Once the calibrations are done, the data integrity is ensured by the alignment checks between interface signals as required by the protocol. In the following slides, we will see some of the snapshots which were taken once the read and write calibrations were done and in the presence of the effects applied by the channel model. In this figure, we can see that there is the ideal signal DQ, which has been skewed by a certain amount provided by the user. In this particular figure, we can see that the DQ has its duty cycle varied. For the region 1, the duty cycle has been increased by 20%. For region D2, it has been decreased by 20%. This figure shows the distortion that is applied on the DQ line. So if you see the DQ bit 5, this is the ideal signal without any distortion added. But once the left and right window distortions have been added, we see that the valid window has decreased. You can see the zoomed in version here. This is the original valid window, and this is the reduced valid window once the left and right distortions have been applied. Having applied these skew and distortions, it was our expectation that the calibration would compensate and our checks would pass. But we found that even after following the setup and hold time, the addition of skew and distortion brought forth many issues in the design, which would not have been detected before the silicon was taped out if we did not use the channel model. We caught many issues in the read and write algorithm, calibration algorithm, where the design was not able to compensate the skew and distortion, which was added by the channel model. The alignment checks played a major role in catching such instances of failures. We also encountered incidences where the calibration on its own was fine, but once it was run in conjunction with other design features, we found many bugs. Such instances were caught during the verification stage itself, and it helped us to better qualify our design. What does the future hold for us? We know that the VLSI industry will continue going through rapid changes. The enhanced memory architectures will keep the verification engineers on their toes and keep fueling the need for improvement in the verification practices. It was this need that drove us to develop the channel model and the related checkers for the verification of DDR5 supporting DDR4 3DS memory. The channel model enabled us to find bugs early in the design and to stress test our DOT. So clear was the impact of using the channel model in our DV experience that since then we have used it in the verification of other PHY IPs as well. And why not? Channel model is a generic block as of now. It can be used for verifying other designs which involve the communication between two or more IPs. Is this the end then? No, by no means. The proposed channel model is a very basic one and there is a scope for improvement. It can be modeled using real number modeling and using frequency domains. X models can be used for characterizing the analog behavior in the digital domain. Factors like voltage variation, channel losses, attenuation, and impedance can also be considered in the channel model to create a mixed signal kind of environment. I would like to thank DVCon India for giving us the opportunity to present our paper. And I would also like to thank the esteemed panelists and the participants for attending the presentation. Last but not the least, I would like to thank Samsung Semiconductor India R&D Center and all my co-authors and colleagues for making this happen. Thank you.
Yeah, thank you very much, Shivani. This was indeed a very promising technique for verification. And regarding the channel model, right, there are a couple of questions from the audience. The one question that's interesting here is, did you introduce all the variations in one go, or did you do one step at a time?
The variations, there is the channel model allows you to enable different features simultaneously. And we have tried skew and damage together in our simulations. And but most of the cases you can either try it only with skew or only with damage, or both of them enabled. But you have to keep in mind that whatever design specifications have been told by the designers, that there is a certain amount of damage which can be compensated by the PHY IP. You remain within those limits, or if you are stress testing it, then you do not go to an arbitrarily high value. Yes, you can enable different features simultaneously.
Okay. One other, I think you kind of alluded to this in your last slide. Are these channel models reusable across projects, or is that the intent, to make it like one generic model that can be used across all projects? Or?
Yes, you can use it across multiple projects, because if you are talking about the DDR5, then you have several protocols which have more or less the same interface signals. So you can, since like I demonstrated in the slide, that each interface signal has its own instantiated channel model. So even if the signals differ from protocol to protocol, you have a generic element that you can just plug it between your IP and the verification IP, and then you can have those effects enabled on your interface signal. It does not have to be of a certain protocol itself.
And one last question. Was there any modeling guidelines followed for the bond wires or interconnects for the 3D structures?
No. This is purely digital time domain modeling of the effect. So we did not come up with any capacitive or inductive modeling as of now in our channel model, but it can be done, because at the end of the day, it is all UVM compliant. It has been implemented in the system Verilog. So if you want to implement some models to evaluate the skew and distortion, it can be done. For our case, we simply took the guidelines, like this is the maximum and the minimum limits within which we could apply a certain amount of skew or distortion, and our test bench just randomized within those particular limits.
Thank you very much, Shivani. This was a very good paper, excellent presentation.